The previous video in this series provides a detailed look at echelon segmentation. This video introduces TrueShape descriptors, the local descriptors used by the echelon algorithm. The demonstrations presented in this video are based on frames from a clip of a rotating head shown here. The demonstration begins with a brief tour of the Echelon test bench, a software application developed to verify the theory upon which the Echelon algorithm is based. Here, I'm loading two consecutive frames from the rotating head video shown earlier. The images I'm retrieving will fill the two frame buffers used by the Echelon algorithm to support side-by-side frame processing. Once the frame buffers are loaded, processing is applied to each frame using the setup GUI. The setup GUI allows a separate scale space tree to be extracted from each frame of video, like this. Once a scale space tree has been extracted, the software displays the highest tier in the corresponding scale space image. In this case, tier 54 as indicated here. As with all images, the tree has a single trunk as represented here by this yellow circle. Next, I'll trace this local extremum back to the top tier. In doing so, the software has traced one of the many stationary curves, or branches, that make up a scale space tree. To explain TrueShape descriptors, this demonstration will look at a single descriptor site for the region corresponding to this interface point near the eye. An interface point is simply a local extremum in the first tier of a scale space image. Interface points are the tips of the branches in a scale space tree. Tracing this branch will then lead to the branch's top point as follows. The branch's top point is the last point in the branch, just before the yellow circle disappears. Activating the top point overlay will show that the algorithm has in fact detected the local extremum inside the yellow circle as a top point, as indicated by the green dot. Every top extremum has one corresponding top saddle point. Here, the top saddle point is the blue dot adjacent to the green dot. Turning on the ISO contour line overlay and setting the number of lines to 35 helps clarify the relationship between a top saddle point and its corresponding top extremum. As an aside, the name saddle point arises because the topology around a saddle point is shaped like a horse's saddle. To continue the discussion, a screen grabber will be used to transfer a copy of this scale space tier into Microsoft Visio, as we're showing here. I'll then enlarge the frame for further clarity. Each TrueShape descriptor is extracted from a set of local extrema that share the same top saddle point. Here, I'm adding a blue dot to make it easier to see the top saddle point. The set of local extrema used to establish a TrueShape descriptor are joined to each other by a series of paths that originate at the same top saddle point. The paths I'm sketching are referred to in the literature as relative critical paths. While tracing each path, I'm attempting to follow a course that remains perpendicular to each ISO contour line that the path crosses. Next, I'm going to add a dot on top of the raw data recorded by the Echelon algorithm so that the data can be cut and pasted to another sheet. Here, I'm lifting out the points needed to describe how a TrueShape descriptor is derived and pasting them into a new sheet. In the three-dimensional scale domain, the points and curves shown here lie in the same plane and establish a figurative garden, complete with walking paths. The data is referred to as a garden set. Here I'm extracting the 4 local extrema that make up this garden set. The relative position information in a garden set is embodied in 6 line segments that connect the 4 points to each other, as I'm going to demonstrate. Next, I'll focus on 3 line segments that share the same local extremum. Each of the line segments is a raw or unnormalized TrueShape vector describing the appearance at the local extremum shared by the 3 vectors. I'm adding arrowheads, and next I'm going to lift out the TrueShape vectors and paste them in the adjacent space. TrueShape vectors are inherently stable with respect to lighting and out-of-plane rotation. To achieve invariance to scale and in-plane rotation, TrueShape vectors are normalized. The normalization process is efficient and simple, involving nothing more than taking the ratio of 2 TrueShape vectors sharing the same local extremum. Such a ratio then yields a TrueShape descriptor. A claim to fame for TrueShape descriptors is that they are simultaneously invariant to scale and in-plane rotation while remaining highly stable with respect to lighting and out-of-plane rotation. To be useful, a descriptor must ultimately be able to provide high classification strength in addition to stability. This diagram is intended to help describe how echelon segmentation and TrueShape descriptors cooperate to achieve high classification strength. The diagram will also help clarify the relationship between the spatial domain and the scale domain. The face image shown here represents the spatial domain. The spatial domain is the first tier in a scale space image. It contains the shape information that we see in images. The volume above the spatial domain is the scale domain, indicated in this diagram by a scale axis, shown here. This is an actual unified feature region corresponding to the face, shown here. Every feature region in an image manifests as a separate stationary curve in the scale domain. This is the stationary curve for this feature region. This is a plan view of the TrueShape descriptor that was derived earlier. This shows a perspective view of the same descriptor approximately as it exists in the scale domain. This stationary curve links the descriptor to a single feature region in the spatial domain. Each of these additional TrueShape descriptors is also linked to the same feature region by the same stationary curve. The main point is that stationary curves in the scale domain tie multiple TrueShape descriptors to the same feature region in the spatial domain. This allows TrueShape descriptors to be ganged together or cascaded to achieve high classification strength. The relationship between TrueShape descriptors, stationary curves, and unified feature regions depicted here is so useful within the context of computer vision that it is not unreasonable to expect a similar relationship to exist in biological visual processing. This segment of the video presents measured data demonstrating the stability of TrueShape descriptors with respect to out-of-plane head rotation. The data to be presented was measured by manually drawing TrueShape vectors on top of raw scale space data as I'm showing here. The process was then repeated for the same feature region across multiple frames of the rotating head video shown earlier. A complete example data set for one feature region is shown here. The raw data set just presented is summarized in this graph. The analyzed feature region for this graph corresponds to the area just above the left eyebrow, as indicated here, across multiple frames from the corresponding video clip. The data indicates that the underlying TrueShape descriptor remains usefully stable over 45 degrees of head rotation, as shown here. The stability reflected in this data represents typical performance for TrueShape descriptors. As a point of reference, no other descriptor in the literature comes close to achieving this level of stability versus out-of-plane rotation. For example, descriptors such as SIFT, HOGS, 2-bit binary patterns, and others only remain stable over a few degrees of out-of-plane rotation. The data shown here corresponds to a TrueShape descriptor exhibiting usable stability over an astounding 92 degrees of out-of-plane head rotation. This measurement, while somewhat atypical, is consistent with the theoretical prediction that the upper limit for stability versus out-of-plane rotation is 120 degrees. This video concludes with an intuitive interpretation of how TrueShape descriptors encode arbitrarily complex shape information. Shown here are two TrueShape vectors that make up one TrueShape descriptor within a given scale space tier. The magnitude or length of each vector can be regarded as quantifying a relative size proportion among three adjacent feature regions, each represented by a separate local extremum, as shown here. As a reminder, the feature regions belong to a face that resides in the spatial domain. Continuing the discussion, the angle component of a TrueShape descriptor, indicated here, encodes how adjacent feature regions are oriented with respect to each other. Arbitrarily complex shape information then becomes a compilation of visual proportions across multiple scales. This multi-scale compilation idea is clarified using this diagram presented earlier. Each group of three vectors represents a pair of TrueShape descriptors, or equivalently, a pair of visual proportions. To help explain the next point, I'm moving all the measured visual proportions corresponding to one feature region into the spatial domain. Next, I'm deleting the corresponding stationary curve. Within the confines of a 2D image, all visual proportion information is compressed into one image plane, the spatial domain. Without further insight, this represents an intractable situation and is the reason that computer vision is a non-trivial problem. The Echelon algorithm expands an image into a multi-tier scale space image, which unpacks the image's stable shape information in the form of TrueShape descriptors. The end result is a theoretically unified framework that enables fully generalized all-view object recognition with the promise of rivaling the capabilities of biological visual processing. Thank you.